Good morning to everyone. Today I am going to discuss about UJT, Uni-junction Transistor. Okay, Uni-junction Transistor. The Uni-junction means it have only one junction, that is PN junction, and it is a three-terminal device. The three terminals are nothing but base 1, base 2, and emitter. And this unit junction transistor is separate or different in working than the BJT bipolar junction transistor, field effect transistor, and metal oxide semiconductor field effect transistor. And here the UJT is only a single PN junction, but it is not a diode. It is a transistor. It is having three terminals. Okay, the three terminals are nothing but base 1, base 2, and emitter. Now I'm going to discuss about the how the construction of this UJT is formed and how those terminals such as base 1, base 2, and emitter terminals are formed. Let us go through the discussion about the construction of UJT. Right. So here let us see that it is the basic structure of UJT, and this is the symbol of UJT. Let us see here how it is formed. What is the procedure here to form these three terminals and one junction and two layers. Okay. First of all, I want to take one silicon bar here. Okay. So this is a N-type material. It is lightly doped material, right? And this is the base surface of the surface of base surface of the particular silicon bar. Okay, this is the base surface of the silicon bar, and the two ends of this lightly doped N-type silicon bar, the two ends here are taken out as terminal is base 2, and at the other side here I want to take it as another terminal, that is base 1. Okay, I want to take another layer here, that is p-type layer. Okay, so to form the third terminal, that is nothing but emitter terminal. Okay, so here this p-type material is nothing but it is heavily doped material, and in between here these are the two layers, p-type and n-type, is form a PN junction, right? And here the n-type material is lightly doped material, and it is having a high resistivity property. And here the p-type material is having, it is highly doped material, means it is having a low resistivity property. Okay, so this is the basic construction of our UJT. Let us come into the symbol of UJT. Here, let us see this is the emitter terminal, this is a base terminal, it denoted as B2, and it is a base 1 terminal, denoted as B1, and this is the emitter terminal, denoted with the E. This is the arrow. The arrow shows the which is make an angle with the vertical line of N-type material. It is lightly doped N-type material. This arrow and this arrow shows the flow of current, flow of conventional current. This is the basic how it is formed as a UJT, and this is the symbol of UJT. Where you can use this particular device, you should follow the the symbol in such a way. If you change any directions or any terminals in the position, it is not correct. So you should follow where you can use for the implementation of any circuit. You should follow that logic symbol is in this way, right? Next. So here, let us see here. Here, the RB2 and RB1 are the base internal base resistance of the silicon bar, and also called as base resistance, inter base resistances of silicon bar. Okay, so this is the logic symbol, and this is a equivalent circuit. So here, the UJT is having a single junction means it is the PN junction diode. Here it is, and these are the internal base resistance of the silicon materials. Here it is called as a interbase resistances, and here RB1 is variable resistor. If you are any applied voltage here, due to the voltage, it may be changing its values. So that value like it is 4 kilo ohm to 4 kilo ohm to 40 ohms. 40 ohms. Okay. So it value may be variable 4 kilo ohms to 40 ohms or 40 ohms to 4 kilo ohms. That will be depending upon the applied voltage in between emitter to base 1. So the total interbase resistance of silicon bar is RBB equal to RB1 plus RB2. Okay. So here, let us see the points here. So here, let us consider the RB1 and RB2 internal resistance of the base region, that is called interbase resistance. Hence, the resistance as RB1 is variable resistance. Its value is variable by applied voltage between the emitter and base 1 terminal. Right? Next, intrinsic intrinsic standoff ratio. Right? So here the intrinsic standoff ratio is denoted with the eta. Intrinsic standoff ratio. So here, if this is the circuit diagram of UJT, let us see here. This is the voltage in between emitter terminal to base 1, and this is another voltage here, that is VBB in between base 2 to base 1. And here this voltage will be drops across this RB2 and RB1. And this much of voltage, this much of resistance will be variable, that will depending upon the applied voltages in between emitter to base 1. Okay, and here, so that voltage will be V1. How much of voltage will be drops across this voltage, across this resistance, that is RB1, that will be denoted with the V1. Okay, after finding this much of voltage here, finally that value is eta VBB. This much of voltage will be drop across this particular resistance RB1. Okay, and this is the emitter current flowing, that is the conventional current if the diode is forward bias condition, and it is a reverse saturation current if the diode is going to reverse bias condition. This is the reverse saturation current. If the diode is a forward bias condition, so this much of conventional current is flowing like this. So before going to the complete operation of this particular equivalent circuit, let us see the voltage across. Let us derive the voltage, how much of voltage will be dropped across this particular variable resistance, right? So by applying here, then the VV equal to 0 volts means it is a act as a open circuit. But here this voltage will be applied in between base 2 to base 1. By using potential dividing rule, VRB1 means voltage drop across the resistance RB1 equal to RB1 by RB1 plus RB2. This is the voltage divider rule into total voltage VBB, right? But here RB1 and RB2 are inter-base resistance of the silicon bar. So RB1 and RB2, here we are taking it as RBB, nothing but total resistance of the total base resistance of silicon bar. And here VRB1 equal to RB1 by RBB into VBB. So this value here, you can take it as eta. So V1 equal to, therefore V1 equal to VRB1 equal to eta into VBB. So therefore eta equal to RB1 by RBB is the intrinsic standoff ratio, right? So this much of voltage is dropped across this particular variable resistance when the emitter voltage here it is open. Okay. So here if V0 means V is open, then the VBB is applied between base 2 and base 1. By this process, we can derive the how much of voltage will be dropped across this particular resistance, that is a variable resistance here, right? So this is the voltage drop across this particular variable resistance, and this voltage will be connected here. Then the diode will be going to reverse bias condition. Let us discuss in next slide. Okay, here UJT operation, right? This is the voltage here, external voltage, that is VBB in between B2 and B1, and this is the VEE voltage in between terminal E2, terminal B1, right? So by applying this voltage and by applying this voltage, what is the output characteristics? We have to understand that, right? So here, so this the voltage across this RB1 is eta VB plus VDD plus VD is this much of voltage is dropped across this particular diode, right? So initially it is some slight amount of voltage will be applied here, but here the eta VBB is much more by compared to with this voltage. So nothing but VE is less than VD plus eta VBB. So then the diode is in reverse bias condition. Reverse bias condition means there is a slight amount of voltage is flowing across this particular diode, that is IE naught. It is reverse saturation current is going like this, right? And further, if you are increasing this voltage, further you can increase this voltage, and here VD plus eta VBB drop across this device here, okay, across here. So then this condition is exceeding, means V is greater than VD plus eta VBB. So then this much of voltage here, V is this applied at anode terminal, and VD plus eta VBB is at cathode terminal. So here applied voltage greater than the cathode voltage, then the diode is going into forward bias condition. But here the majority charge carriers are injected into the N region, N type region. Then the conductivity of the N type region is increases, means the resistance here it is decreases. The resistance is decreases. Okay, so by decreasing this resistance here, the voltage drop across this particular variable resistance also decreases. Okay, and here the intrinsic standoff ratio is taken it as, that is 0.55 to 0.8. Okay, understand it? It's clear. This voltage is greater than this voltage. This voltage will be applied across this anode, and this much of voltage at cathode, and VE is greater than this cathode voltage, then the diode is going to forward bias condition. The emitter current is flowing, and emitter current is going to increasing order. And here measured charge carriers are, that is nothing but large number of charge carriers here in P side, because of P side, P type is a heavily doped material. Due to that heavily doping, there is a large number of charge carriers. The large number of charge carriers are injected into this n-type region. Then the conductivity of the n-type region is increases. If the conductivity of n-type region is increases, automatically the resistivity of the material will be decreases. So the resistance here it is decreases. So if the resistance is decreases, the voltage drop across this particular resistance also decreases, right? So let us what we are discussing in operation of UJT, those concepts you have to observe in this waveform, right? It is the VA characteristics of UJT, Uni-junction transistor. So here we can observe the three regions, such as one is top region, negative resistance region, and saturation region. So let us see here. So this is the region here. This is the region. In this region, the diode is going into reverse bias because of let us see here. So this voltage VEE is less than the cathode voltage. Then the diode is in reverse bias condition. There is a small amount of current will be flowing across the diode. This is nothing but IE0. IE0. So this is the cutoff region. That is nothing but a cutoff. In cutoff region, the current is going at IE0. And further we can increase that VE value. That is the voltage in between emitter to base 1. Further it is increases. So when this voltage will be equal to cathode voltage or greater than the cathode voltage, then the maximum peak will be the maximum peak value is reaches, then automatically the current is flowing. But here the current is going into decreasing order. Sorry, in increasing order. Increasing order. Okay, it is going to increasing order. Further increases this voltage, the current is going into increasing order. But here the voltage is drop. If the voltage drop in the peak value, that resistance will be decreases. So negative, it is a negative resistance region. So how it is negative resistance region? Let us observe here. Here VE is it is VEE is going into increasing order, and the current is, that is nothing but IE is also increasing order. At the same way, the resistance is also increases. But in this case, so let us see here, VE is greater than that cathode voltage, then the diode is in forward bias condition. The maximum number of charge carriers are injected into this n-type region. Then the conductivity of the n-type region increases, means the resistivity of the n-type region is decreases. Further, increasing this VE voltage in between emitter and base 1, the current is also increases, but the resistance is decreases. But generally, by increasing the voltage, the current is increases, the resistance is drop. Resistance is drop. Okay. So here it is the negative, to that it is a negative resistance. Negative resistance voltage, negative resistance region. So this is point here, it is VV, valid point. And further it is the voltage will be increasing and this is nothing but the device is going into saturation region, right? And the applications of the Uni-junction transistor is mostly it is used in relaxation oscillators and triggering circuit and timing circuit.